This video is about an introduction to functions. Now, this is in the context of an intermediate algebra course, and this is often the time where a strict definition of a function is introduced, though, as you'll find soon, the concept of a function and some of the algebra involved with it is not new or won't be new. But we're just going to talk more specifically about the behavior and relationship between some things we may have already seen. We're going to begin with a definition, and that is this. A function is a relation where every input has exactly one output. So it's often thought of as an input-output machine. You can use the illustration of a vending machine. And it's simply that. Every input, in this definition, every input has exactly one output. So you put one thing in, you get one thing out. That's the strict definition of a function. Now, in this introduction, we're going to go through several different ways you can represent functions or even just relations more generally and see how they interact with this definition. One of the first ways we could discuss is what's called a map. And a map is a good conceptual way to understand a function or a relation, but it's not very practical when it comes to actually doing algebra with functions. So eventually we're going to move away from it and use other notations. But it's a good conceptual understanding, and since that's where we're starting, we'll begin with this. Now, we're going to go through three distinct columns in a chart here and use them as examples. In the first column, the first row, we're going to call this picture we see the letter F. Just have a cursive F here. And this picture really has two kind of ovals. The left one is labeled input, and the right one is labeled output. And then inside the input oval, we have three items, the letters A, B, and C. And inside the output oval, we have three numbers, 1, 2, and 3. And then there's a connection between the input and output, denoted by arrows. So we have an arrow that says A goes to 1, B goes to 2, and C goes to 3. You could say those are mappings distinguishing, how these inputs and outputs are connected. Now, we'll go one certain example at a time and kind of go down the column per example. So we're dealing just with F here primarily, which we just described in its map form. There's another way to represent what we just looked at or discussed in the map form, and that is with set notation. Set notation involves usually these curly braces, or curly brackets, you may call them. And in set notation, you're just collecting a bunch of elements. Well, the elements involved in this set inside these curly braces are going to be ordered pairs, which basically distinguish or designate each arrow. And so since our first arrow in our map had A pointing to 1, the first ordered pair in our set is the ordered pair A, comma 1. So it's kind of like an XY coordinate pair that you're used to, maybe from a graph, except we have just these specific designations as defined above in the map here, right? So A went to 1, so we have A, comma 1. B pointed to 2, so we have the ordered pair B, comma 2. And C pointed to 3, so we have, of course, C, comma 3. That's a set notation version of the same kind of relation we have illustrated in the map above it. Now, when you look more specifically at some of the pieces involved here, you can discuss what's called the domain, which is known as, or it's described as the input. And typically that's designated as the x variable in a typical xy coordinate plane. So input, which you could say is x. And so if I wanted the domain of the relation I have defined way above, that would be the set of only the input values. So we have just A, B, and C as those individual letters listed from our input originally way up where we defined it in the map. Now, this is the set notation way of describing a domain, just listing the elements, but that's because we only have three of them. There are more robust ways to describe an infinite number of elements, as we'll get to shortly. But so far, just using set notation again here, A, B, and C would be the domain. Now, the range, moving on, is the list of the output values, typically denoted with the letter Y in an algebraic coordinate plane. So in this example, again, the outputs are just the simple numbers 1, 2, and 3. And so we have in set notation here just a list of the numbers 1, 2, and 3 in curly braces here. Alright, so that's several ways to represent this first relation defined way above by this map. We'll move on to a second and third, and then we'll go back and discuss some more function-related definitions to these. Let's describe our second relation as the letter G, just to be able to distinguish these. And in this one, the input contains the letters A, B, and C. The output contains the letters 1, 2, and 3. This time we have A going to 1, we have B also going to 1, and then we have C going to 3, again denoted with these arrows in the map kind of notation. The set notation will have, as we've seen already, just the ordered pairs representing each arrow. So we have A, 1, B, 1, and C, 3. And then the domains and the range in set notation will be the same as they were originally here because they all are the same, inputs being A, B, and C, and outputs being 1, 2, and 3. So again, domain is input, range is output. Thirdly, our third example, we'll call that one letter H, just to be able to distinguish what we're talking about. The input there and output, same thing, A, B, C for input, 1, 2, 3 for output. This time we have A going to 1, A also going to 2, B going to 2, and C going to 3. So the set notation follows this. We have the ordered pairs A, 1, A, 2, B, 2, and C, 3, just going again one for each arrow in the map. Of course, domain and range are the same for these as well. Now, going back through this, let's discuss a very important application. We just defined above in our notes what a function is. So our question is now, do any of these relations define a function or represent a function? Remember the definition we have above is that for a function, every input has exactly one output. So if you look at each of these relations, go ahead and pause the video if you want to take a minute to decide, do any of them represent functions according to that strict definition? If you consider the F relation, the first one, every input does have exactly one output. A, B, and C go to 1, 2, and 3 separately. Which means, yes, this fits the definition of a function. We could say that that first relation is a function. And notice you could even determine the same thing by looking at the set notation because there are three distinct elements in it, A to 1, A, 1, B, 2, C, 3. Again, matching up the arrows. Let's go on to the second map. We had G. In this one, we have A going to 1, B going to 1, and then C going to 3. So notice what's different here. We have A and B going to the same output value of 1. We have the output value of 2 not even used. And then we have just C going to 3. So the question is, does this fit the definition? Again, pause the video if you want to think for a second. If you think carefully, of course, the fact that A and B both go to 1 is usually where people are kind of drawn, saying, I'm not sure if that fits. But the definition specifically says that every input has to have one output. So think about this. Does the input of A have one output? Yes, A goes to 1. Does the input of B have one output? Yes, B goes to 1 as well. Does C have one output? Yes, C goes to 3. Now, the fact that A and B both go to the same output does not ruin the fact that they each have one output. A goes to 1, B goes to 1. They each have 1, which means, again, we could say, yes, this represents a function by that definition as well. And even in its set notation form, notice you can tell A and B both go to 1. We have A, 1 and B, 1, but again, that doesn't violate the definition, so we're fine with that. If you go to the third example, relation H, in this one, we have A going to 1 and A going to 2. Well, you may be able to catch quickly here. This violates the definition. We're going to have to say no. This is not a function because the definition above said specifically every input must have exactly one output. That means exactly one, not two. But the input of A has two outputs here. A goes to 1 and A goes to 2, so this violates the definition. Notice even in set notation you can spot it. It's where A goes, we have A comma 1 and A comma 2. The same input should not have two different outputs, showing why this is not a function. Now that's just some ways to represent functions. Again, we're going to get more into the algebra of them that will eventually use some more useful notation. Speaking of which, let's next discuss what's called function notation. This is really, really common with functions, and it works as follows. I could say f, actually I'm going to refer to the f we have above. That was our first function, our first relation we said was a function, the first column. If you see notation that looks like f and then open parentheses immediately following it with something inside them. So we have f and then a b, a capital B, inside the parentheses that follow it. And then we're going to say that equals something. Well, here's how this works. When you see f open parentheses, what you see in those parentheses represents the input, and then what it's equal to is called the output. Well, we already have this designated for relation f above. Remember, when you look at function f, we said it was a function. B goes to 2. Input B points to, with an arrow, the output 2. Or we have the ordered pair B comma 2. So we could say f parentheses B equals 2. That's kind of showing you what the input and output are that match. And importantly, the way we would read this matters, especially since usually parentheses are used for multiplication in arithmetic or algebra. So far, that's how we've been using them. This is not that. This is called function notation. It actually means something. The way we would read it is to say f of b equals 2. So it's not f times b, it's f of b. It's telling you that b is the input to the function f, and then the output is what it equals. Let's try now to work with an example along with this notation. This one says we're going to let f of x, so that's a way you can usually denote a function, f of x, that's the function notation, equals, now we're defining it as 3x squared plus 4x minus 2. And then we want to find the following. We want to find firstly f of negative 2. So this is using the function notation we just wrote out, where it's f and then parentheses containing negative 2 immediately following it. Again, this is not f times negative 2, this is f of negative 2, which means we're putting negative 2 as the input into the f function, which we've just written out, defined above, given in this problem. So to plug a number in, we're going to do what we've always done in substitution, which is write out the function but with blank parentheses. So instead of 3x squared, as our function begins, I'm going to write it as 3 blank squared, where we have blank parentheses with the squared after them, and then plus, instead of 4x, we'll have 4 blank, and then minus 2 to finish. If we want f of negative 2, we simply want to plug negative 2 into now all the blanks that we've written out in our function. This is the safest way to substitute for a function or really any expression, and trust me, you will definitely want to use these blank parentheses with what's coming. They really do help prevent a lot of mistakes. Now all we do is simplify the arithmetic here, so that means we have 3 times 4, negative 2 in parentheses, squared is positive 4, so 3 times 4, and then it'll be a minus 8, and then a minus 2. Ultimately, that's 12 minus 8 minus 2. 12 minus 8 is 4, minus 2 is 2. So ultimately, what we could say is that f of negative 2 equals 2. Let's try another example of the same type. This second one is listed as we want to find f of 1 plus f of negative 1. Well, we've already defined f above. We're just going to keep using this one. That was the function given that we read before the previous problem. That was the 3x squared plus 4x minus 2. So same function, but this time we're doing a couple different input terms here. So we want, first of all, f of 1. Well, as we just did, we want to basically write the function out but with blanks, and then plug 1 in those blanks for this f of 1. So instead of 3x squared, we'll say 3 blank squared. Instead of 4x, we'll say plus 4 blank, and then minus 2. So that's the function written with blanks instead of x's, and because of this first term here being f of 1, we want to put a 1 in each of those blanks. Now, the second term was f of negative 1, and we're adding this with it. So then we'll say plus, we want to copy out the same function, but start over with blanks. So it's 3 blank squared plus 4 blank, and then minus 2. But in these blanks, this is now f of negative 1, so we put the negative 1 in the blanks. And then ultimately, we're going to want to simplify all of these terms just using general arithmetic. So this would be 3 times 1 squared is just 3, plus 4 times 1 is 4, minus 2. Moving on, we'll say plus. In the second term here, we have this 3 times negative 1 in parentheses squared. That's really just 3 times 1, which is 3. And then it'd be minus 4, minus 2. Now we'll just combine all this arithmetic. It should result to just 2. Let's try another example, which will actually allow us to introduce a very important definition along with it. For this example, we're going to so we're just kind of creating a function here. We're going to let g of x, so that is in function notation, g parentheses with an x in it, equals, so g of x equals a fraction where the numerator is 3x minus 1 and the denominator is x minus 5. Alright, so given that function, we're going to begin with a definition, a very important one, which is this. The domain of a function, now we already mentioned that above, but hold on here. So the domain of a function is the set of all values we're allowed to plug into the function. We already mentioned above that domain is associated with input, and that fits this definition. But now we're going to get a little more specific regarding the algebra. Remember, into is typically the x variable, and the output, the range, is typically the y variable. So in the definition of domain, we want to list or somehow describe all the values we're allowed, notice allowed, to plug into the function. Well, you may ask, well, what wouldn't we be allowed to plug into a function, right? What kind of number? Well, so far, we'll say a domain is all real numbers except the following. So, good question. What wouldn't we be allowed to plug in? We're going to say we can plug in anything we want except anything, any numbers which cause division by 0. So as you may recall from arithmetic, we cannot divide some number by 0. Like 2 divided by 0 doesn't make any sense, it's undefined. And so it would make sense that to define a domain, we wouldn't be allowed to use anything that might cause this particular problem. So, for example, in g of x defined above, remember, we said way above, g of x was 3x minus 1 over x minus 5. That was defined as a fraction. So in that function g of x defined above, the domain is all real numbers except x equals 5. Because, think about that, if you go back up to where that's defined, if you were to plug in 5 for x, look at the denominator. It would be 5 minus 5, which is 0, but we can't have that. So there are a couple ways to represent that, and the interval notation is the way we're now going to write it first. That would be using interval notation to describe all real numbers except 5. The way we do that is negative infinity, representing the left boundary going on forever to the left, comma, and then 5. We have to kind of hit the brakes at 5. Now we don't want to include 5. We're going to put a curved parenthesis as the boundary for 5. So we have curved parenthesis around negative infinity on the left side, comma, 5, right parenthesis, curved. We want to hop over and not include 5. So we're going to union that set, which is everything to the left of 5, with everything to the right of 5. So that would be open parenthesis, 5, comma, positive infinity, and that represents everything after 5. So this is basically everything except 5 in interval notation. It's a very common way we'll be using to describe this kind of number set. Now, of course, you can use set notation as well. And one way to use that would be to say, I want to use a curly brace here, and then I want all x's, so I just put the x variable, and then I put a vertical bar saying I want to now describe what those x's are, and then I would say x is not equal to 5. So x, and then literally not equal, slash through the equal sign 5, close the curly brace. So that's a set notation way of saying, give me all x's where they're just not equal to 5. Again, a way of representing the same thing, which is all real numbers except 5, the domain of our example function listed above.